speaking at the KCDC. Is that right?
Yeah.
Coming up, so I'm just gonna hand it over to you. And yeah, rock and roll, man. Thanks.
Thanks. Out of curiosity, are many of you going to attend KCDC as well?
What's that?
Are many of you going to attend KCDC as well in the coming days, starting tomorrow?
KC Developer Conference.
Okay, so well, I'll be there as well. I'll be doing 2 Docker tutorials and a talk. I don't remember which one it is. So for today, I want to talk about the Docker storage drivers, but actually there are only 2 parts in that talk. I have one part about Copyonwrite because I wanted that talk to be interesting even for people who don't care about Docker, and I want them to be able to walk away and say, okay, there was a lot of stuff about Docker, but I don't care about containers. However, there was a part about Copyonwrite that was still interesting. And at the same time, I wanted to have something directly useful and actionable for people who care just about Docker. So onwards. Short intro, so I'm Jerome, I work for Docker, and so I usually can be found in San Francisco when I'm not traveling to locations like here or in the beginning of the week on the East Coast for the Red Hat Summit or other conferences. As you probably guessed from my accent, I'm French, nobody's perfect. And before doing that for Docker, I was working on .cloud, which was like the previous name of Docker. So that gives me the unique chance of having like almost 5 years of Docker experience, even though Docker is only 2 years old. That's great. And so the outline for today, first I will do a really short intro to Docker, but that's really like if you've been living under a rock and never heard about Docker, I want you to still be able to get something out of the rest of the talk, so I have to make a really short intro about it. Then I will talk about Copyonwrite. Then I will give a little history, a timeline of the Docker storage drivers. And then I will go over each of them and describe their pros and cons, how they work and their differences. So first, the short intro to Docker. So Docker is a platform that is made of an engine, like the Docker engine. It's an open source hypervisor for containers, if you will. You run that on a Linux machine, and then you can run containers on that machine. And then another part of the Docker platform is the Docker Hub, which is an online service that lets you store images of containers. If you can liken that to Git and GitHub, like the Docker engine is open source, it's free, you can use it without paying any money to Docker Inc. In the same way you can use Git, it's open source, it's free, and you can use it on thousands of servers without paying anybody. And then you have GitHub that makes Git kind of more interesting and useful in some ways. It gives you a nice web interface, it hosts your repositories. So with Docker, there's a Docker Hub that has a CNR role. You can host container images there, there are a bunch of services around it. That's pretty much it. Okay, so there are longer intros to Docker available pretty much everywhere, but what I want to show here is this little example. I don't know if it's really readable from where you are, but this is an example of a tiny Docker session. We're doing docker run, -ti, Python, bash. When we do that, we tell to Docker, hey, please start a new container using the Python image and start bash, a plain old shell, inside that container. Then we are in the container and we do pip install IPython. Pip is the Python package manager, so we tell it, okay, get the IPython package, download it, install it, and then in that container we can run IPython, which is a slightly better interactive shell for Python, among other things. So when we did that, we created a container like from scratch. It has its own file system, it has its own network stack, and its own IP address, its own everything. It's almost like a small autonomous virtual machine. And we started the bash process and we installed IPython. Now let's look at what we did not do here. We did not make a full copy of that Python image. When we do docker run Python, we run in a container that has that is based on the Python image, but we did not make a full copy of that image because that would be slow. Even if that image is only a few hundreds of megs, that would still take a few seconds, while here when you run that command, it's instant. It's like docker run, boom, and you are in the container immediately. And at the same time, we are still kind of working on a copy of that Python image, because when I did pip install IPython, I'm installing IPython in this specific container, but I'm not changing the original Python image. So on the one hand, it's as if I were making a copy because I'm not changing the original Python image, but it's not making a copy because it's fast. And it's fast because it's using Copyonwrite. And that's a very important thing because that lets us have something that looks like a copy but is not a copy. And so it lets us save a lot of disk space, because instead of making that 200, 300 megs copy, we are just working on a tiny, just on the changes made to the container, and also saving a lot of time since we don't have to actually copy those bytes. Copyonwrite, let's try to find a definition for that. It's a mechanism allowing to share data in a way that it appears to be a copy, but it's really a reference to the original data. And the real copy happens only when someone tries to change the data. So it's as if I were giving you some data and saying, okay, it's yours, you can change it if you want. But it's not exactly yours. It's only when you will try to change it that the real copy will happen. And there are a few metaphors to explain that. The first one is to imagine that you have like a whiteboard and you put some tracing paper, you know, this transparent paper, and you can draw on the paper, and whenever you want, you can remove the paper and you get the whiteboard that was behind it. So you make your changes on an extra layer, and the original is not changed when you draw on the tracing paper. Another metaphor is it's as if you were borrowing a book from a library, and we are telling you, if you want, you can make notes on that book, you can like scribble on the pages, that's fine. It's as if it were your book. But in fact, instead of giving you an actual book, you get a kind of a magic book made of shadowy pages, and whenever you are about to write on that book with your pencil, at that very moment a magical gnome shows up and takes the book, or rather just the page, and makes a Xerox copy of that page and gives you an actual sheet of paper. That's really what happens under the hood with Copyonwrite. There is something that will detect just before you're going to write, and at that very moment we will make an actual copy. But the rest of the time, everybody is looking really at the same page of the original book, so that you don't have to make full copies. Another metaphor, which is more about like allocation on use rather than copy on write. You can imagine that you have a very, very, very long, like an infinitely long street. And so you have house numbers from 1 to infinity and beyond. And you tell to someone, you can buy a house on that road on any address. You tell me like your favorite number, it's 4242, fine, you get the 4242 house on that street. And when you actually get there, at the moment when you kind of step inside the house, that's when they actually build the house. So you can pretend that you have a very long street with lots of houses, or you can pretend that you have a lot of memory with some data in it. And whenever you actually want to get into the house or use that memory, that's when it actually gets built or allocated. So how does it really work? So obviously magic is involved, but seriously, I will explain really how it works. But before, I will just mention that copy and write is everywhere. Like when you are in the shell and you do ls, copy and write happens, because on a Unix system, when you want to start a new process, you don't just say, okay, let's start ls. No, the only way to create a new process on Unix is to make a copy of an existing process. So the existing process goes through a kind of self-replication mechanism, and so you have like your shell, and when you do ls, under the hood what happens is now you have two shells. One is the parent process, and it watches over the other one, and the other, the child process, will exec, so it will replace itself with ls. That can sound a little bit complicated, like I just want to get ls, what should I want to make a copy of my shell process, and then that copy will replace itself. Even if that sounds a little bit crazy, that's actually way simpler to do things like that, because it gives us a lot of other mechanisms to share file descriptors and so on between the parent and child process. But so basically, just when you do ls, copy and write happens because you're making a copy of your shell. And here we're using copy and write. And by we, I mean the operating system, because we don't want to make full copies of the process when each time we create a new process. Another example is to obtain consistency snapshots, and I will talk a little bit more about that. VM provisioning and obviously containers. Let's look at those use cases a little bit in depth. So process creation, I mentioned that. We want process creation to be fast. So when you make a copy of an existing process, we want to use copy and write so that we don't have to copy like gigs and gigs of RAM if that's a really big process that we're forking. Memory snapshots, so that's almost the same thing. I would say, okay, why are we bothering like with making a copy of the process rather than just starting ls and that's it? Because this mechanism gives us some really nice features. Maybe you know about Redis. Redis is an in-memory data store, and with Redis you can so you have a kind of database. It's not SQL, it's NoSQL, it's just key value. It's in memory, but you can dump it to disk. When you do a save on Redis, so when you ask to Redis, please save everything to disk, it will be consistent. This means that if you, let's say that in your Redis database, let's say that it spans from here to here, like all over here, and you have a bunch of bank accounts, and you are doing transactions, so you're taking money here and putting the money here. You want to make a save in the middle of that. So you do a save and you're doing transactions and you reach like maybe the middle here. And then you have a transaction showing up, so taking money here and putting the money here. If Redis was not careful at all, you would copy that to disk. So here I have the bank account on disk with the old amount. Then I take the money here, put the money here, and I finish my save operation. And now on disk, I still have my original bank account amount here, but the new updated bank account amount here. So I basically created money, which is great if you need some money, but not so much when people start looking into the ledger and say, hey, what's going on here? So we want to have a consistent snapshot of the data. We want to say, okay, we want to be able to take a kind of picture of the whole data at one point and save that on disk, not like the amount of 5 minutes ago and the amounts of 5 minutes later. So there are multiple ways to do that. One way is to say, okay, stop, we're doing a save. So during the save, we're going to block all transactions. That's not really cool because it means that when you have things using your Redis data store, everything is blocked because you're saving data to disk. The other way is to use copy and write. So with copy and write, you say, okay, I have my Redis process. I will fork it. So now I have two Redis processes that are exactly identical. They have the same memory. And one of them will go and do the save command, and the other will continue to serve requests. And when I have a change, when I have a transaction, I am changing the data in the Redis that serves transaction, and then the system does copy and write, because I have two copies of Redis that are real copies but not real copies. Like they start being identical, but when you make changes in one of them, the other continues to live its own existence. So basically, you can have one copy of Redis saving to disk and the other continuing to save requests. Making the initial copy, even if your Redis data store is huge, is extremely fast. And the memory actually gets copied only when you make changes to little chunks of memory. So that's really useful. So another example for that is memory mapping. So with memory mapping, so here that's the metaphor about the houses. You can take a huge file, even if it's like terabytes big, and you can map it in memory. When it's mapped in memory, it's as if you had allocated the amount of memory required for the file and loaded the entire file into memory. you have something in memory that looks like it's a huge buffer containing the file in full, but it's not. It will load it on demand. Whenever you try to access some place in that buffer, then it will say, okay, now I have to really load the data from the disk. That's how it works. So how does it really work? So what's the magic? What are really the little gnomes? There is something called the MMU, the Memory Management Unit, and that's the little gnome that gets to intercept your pen just before it hits the page. Interestingly, we also call that memory pages. So the MMU is a kind of a middleman for all the memory accesses, so between the CPU and the physical memory. It does the translation between logical and physical memory, but let's forget that for now. But more importantly, it enforces access control. So for each zone of memory, they have some permissions, like you can read, you can write, you can do both, you can execute it. And whenever there is a memory access, it goes to the MMU, and the MMU gets to approve or deny that access. So if it's approved, okay, it goes through, done. If it's denied, then you get what we call a page fault, which is something trying to access some chunk of memory, but really it shouldn't. So let's see what can happen here. If I'm reading some private data, that's fine, I can go through that. If I'm trying to read some shared data, that's fine too. If I'm writing private data, so far so good. Now if I'm writing some shared data, that's when you say, okay, stop, wait, I have to duplicate that little amount of data. So I have a page fault, it goes to the operating system. The operating system looks at, okay, what's going on here? Okay, you're trying to write to shared data, so I'm going to duplicate that so that you can have your own private copy. And I will let the operations resume so that you can write to this private copy and pretend that nothing ever happened. You have other scenarios. Do any of you write some C code sometimes, or had done that in previous lives maybe? Some people. So you know what segfault is, right? It's when you kind of screw up the memory location, and that's actually what happens when you try to read or write to an area of memory that kind of either doesn't exist or is not made for reading or writing. Then the MMU says, okay, that you try to do something you could not, so it tells that to the operating system, and the operating system say, okay, this is not a Copyonwrite area, this is not like a memory map, this is, okay, you try to read or write to a zone of memory that doesn't exist. So I'm going to kill the process with either segv or segbust, not segbug, but segbust, there's a typo here, depending on the circumstances. Okay. So that's how it works for the memory, because there is some special little chip, now like bundled within the CPU, to deal with that. Now, another example is when we want to have consistent disk snapshots. So it's exactly the same idea as the Redis example, but for a regular on-disk database. Like, let's say you have MySQL or PostgreSQL database running. It's very busy, it's changing all the time, but you want to make a backup of that database, and you want to do like a plain old backup, like a tar file of the files on disk. But the database is so big that basically between the moment when you start the backup and the moment when the backup will end, a lot of things will have changed. And if you're partially unlucky, your backup can be corrupt because the tables that you set in the beginning have been rewritten by the moment that your backup is gone. So again, you have the choice. You can say, let's stop the database, make the backup, restart the database. Not so good for uptime. Or you can use, well, most modern databases have mechanisms to do clean backups like that, but you could also use disk snapshots. If we're talking about a special database that doesn't have a way to make a clean dump of the data, which was the case at some point for MongoDB, like in some scenarios you have some big collection, when you try to make a backup of that, it just doesn't work. So then you can say, okay, can we like take a picture of the state of the disks like as they are right now, and we can use that as the backup. So you want the same idea on something that looks like it's some disk storage, but you want to be able to take a snapshot, take a picture of that, and save that snapshot while writes continue on the disk themselves. And that is Copyonwrite on disks, and it was initially implemented using NAS or SANs, which are big racks full of disks and with a fancy controller that deals with that. Because obviously when you have that, instead of just having this is a disk, so it has bazillions of disk blocks, and I'm just mapping this area of those blocks to this disk and the next area to another disk and so on and so forth. Now you have to deal with those snapshots. So you have to keep track that this area maps to those disks, but now there is a write coming here and it's part of a snapshot, so I have to divert that write to another disk and keep track that in snapshot number 55 that block is actually somewhere else. So it's much more complicated, and initially it was implemented in separate storage systems because our puny little computers were not powerful enough to deal with that. Things have changed a lot. Not just thanks to VMs, but among other things. About a decade ago, when people started to use VMs for hosting, they realized that pretty much everybody, or rather like if you're like one hosting provider, you would have a very big chunk of your customers would have exactly the same stuff on their disks. You would have, that's sad, but 90% of the people out there would be deploying WordPress on Fedora using the same version of PHP and Apache because somebody had the brilliant idea of writing this tutorial and everybody decided to follow that tutorial at some point. And so they all have exactly the same packages, the same things installed, so that's a lot of wasted disk space, a lot of repetition. And so the idea here is maybe I could use this Copyonwrite thing. Maybe as the hosting provider, I could give them like a template, like a good, like state-of-the-art WordPress install, and I give that to them. And now everybody gets that same install, and they're happy because it's faster to install that just going through the steps of that tutorial. And for me, it's great because I'm giving, let's say, 10 gigs to each customer, but really, on the first boot, those 10 gigs cost me 0 because everybody is using the same 10 gigs of space. I have like one image and everybody is actually using the same image. And as they start to write on their disks, that's when I pull free blocks and I give them blocks of free space. But the end result is that if everybody only writes like, let's say, 10, 20, 50 megs, 100 megs of content in the WordPress setup, then I need to only give them 100 megs of disk space on my filers and everything instead of 10 gigs. So the savings are huge. That kind of technology, so LVM on Linux, on Solaris there was ZFS, Linux then had also BTRFS. More recently with containers we started to use AUFS and others. So that kind of technology became more widespread because the advent of virtualization and then cloud and everything made those things more useful for everybody, and that drove them to be more stable and ubiquitous. The fact that it was not only for high-end, super expensive hosting. Yeah. So how does it kind of tie to Docker? Well, that's right. When you do Docker run Python bash, then we would have to make an actual full copy of the Python image, and that would take forever. Maybe not forever for Python, but for Java plus Tomcat plus and so on, that would take forever. We would end up using a lot of disk space. Like I have some demos sometimes and I do like Docker run Ubuntu like 20 times in a row in 2 seconds, and I haven't used up 20 copies of Ubuntu. Each time I'm just getting like a few kilobytes, maybe megabytes on disk, and that's super fast. So without Copyonwrite, Docker would be much more boring or much less impressive because we say, look, I'm starting a container. and get a coffee, and then starting another container and get a coffee. Pretty much the thing that happens when you start VMs on Amazon or something like that. It's cool because instead of having to place an order and get the server like 1 week later, you place an API call and in a minute you have your VM, so that's great. But with containers, we go to the next step, which is you type a command, enter, and boom, your container is here. So that's why Copyonwrite was so important for Docker. I have a kind of thank you slide to some of the people that either started or were deeply involved with some of those Copyonwrite mechanisms. That's very risky because you always can forget somebody, but anyway. So now I want to talk a little bit about the history of Docker storage drivers. So what we had in the beginning, and then why did we add others, like why don't we have just one storage driver and that would be the end of it. In the beginning we had AUFS. So AUFS, I will give more details about exactly what AUFS is, but we were using it because that's what we were using at .cloud. It had some very specific properties. Basically it was very lightweight and very efficient, and so we were running a pass, so we wanted to have hundreds, if not thousands, of containers per machine, and AUFS can do that very well. There is, however, a little problem with AUFS, is that that's not in the Linux official kernel. Like if you download the kernel from ftp.kernel.org, there is no AUFS here. You have to take the kernel, you have to apply a bunch of patches, and we were running a pass, so security was a big concern, so we also were using GRSec and a few other custom patches. So merging all those things together was kind of interesting. Even though AUFS was not perfect, I mean, so the reason why it's not in the kernel, let's talk about that, is because at some point the people who were working on the UFS, so they started the project and they got feedback, they improved it, they started to add a lot of fixes and patches and handle very tricky corner cases, so the code was bigger and bigger, and each time they came to the kernel maintainers to say, hey, can we merge AUFS into the main kernel? It was such a big patch and a huge code base that the maintainer was saying, the hell to the no, I'm not going to merge that, that's too much code, that's too complicated. And they tried multiple times, but there was just no way that this would be merged ever. But yet, many people were still believing in AUFS, so we did back then, but not only us, but also Debian and Ubuntu, and they were using that for live CDs, so not containers, not Copyonwrite, well, kind of Copyonwrite, but the idea here is that when you have a live CD, you know, those are the CDs that you can put in the machine and it boots on Linux, but so it's a CD, so obviously you can't write on it, but it's using some tricks so that you can kind of write anyway, except the writes will not go to the CD, they will go to files on the side, on somewhere on your hard disk or USB stick or whatever, and it's using also some kind of Copyonwrite, except here it's allocate some space somewhere on write. So when you write, instead of writing on the CD, you write somewhere else. So it means that Ubuntu and Debian were shipping with AUFS. So when we released Docker, we could tell people, okay, you need a UFS to run that stuff. So your best bet is to run it on Debian and Ubuntu because they ship with the UFS. The problem is that there were some people that also were interested by Docker and they were not running Debian and Ubuntu. Basically everybody using Red Hat distros. Those kernels don't have a UFS, and those people wanted to run Docker anyway because they wanted to be cool too, and so they started to talk to their Red Hat reps to say, how can we get that Docker stuff on our Fedora and RHEL and CentOS machines? At first, so Red Hat came to us, true story, and asked us, okay, how can we get Docker on Red Hat? So we said, easy, just merge AUFS into the kernel, except, yeah, we all know that that doesn't work. They tried a couple of more times and say, well, can we do something else? And he said, maybe we could use something else, some other Copyonwrite mechanism. Turns out that there are many other Copyonwrite mechanisms, And so Red Hat contributed device mapper, then BTRFS, then overlay. But more importantly, even like more importantly than contributing those drivers, they contributed the, let's say, the framework, the architecture, so that the storage system could be could come as plugins instead of being like one single thing. And that was probably the most difficult part. Not just like adding BTRFS support, but making it possible to change those drivers. That was really the hard part. So yeah, special thanks to two of the Red Hat engineers. Those two guys worked, I don't know, maybe full-time, maybe even more than full-time for so many weeks and months to make all that stuff work. Red Hat really played fair here. It's really like they contributed to the open source project. I mean, some evil companies could have done something like, okay, this will be our own version of Docker that only works on our stuff. No, they really like played by the open source book, so thanks. Now, let's see a little bit how the different storage drivers compare. So first, AUFS. I said this was the original one. It works actually pretty simply. The idea is that you have multiple branches that are completely normal directories, and you are layering them, like putting them on top of each other, and generally you will have a bunch of read-only branches and a read-write branch at the top. Imagine you have a bunch of glass plates like sitting on top of each other, and you have a marker pen, and you can write on the topmost plate. But if you look from the top, you can see what's written on the glass plate all the way to the bottom. So when you're opening a file, you're just looking at the specific location of the glass plate, so you will see what's on the top. So if there is nothing on the 5, 6 first layers of glass, but there is something on the 7th, then you will see that. And that's exactly how a UFS works. When you're trying to open a file on a UFS, it will try to look for that file in the first layer, so the first directory. And if it doesn't find it, it will look in the second directory, the third directory, the fourth, and so on and so forth, until it either goes to the bottom and then the file is not found and it says file doesn't exist, or it finds the file somewhere and it says, okay, the file exists and now it's open. If you try to write, the situation is slightly different. It will also look for the file, but if the file is found, if it's found on the topmost plate, that's okay, because you're willing to write, the file is on the topmost plate, so you can write here. However, if the file is found somewhere in the middle or the bottom, then before being able to open the file, it has to be copied to the top, because you want to change that file. So before, since you can't change the layers on the bottom, you have to copy the entire file on top, and then once it's on top, you can change it. This operation is called copy up, because we copy on top, and it copies the entire file. If it's a small file, that's okay, that is a small config file, that's super fast. If you're opening a big file, like that's a database, or that's a huge log file or something like that, then the first time you open the file, you will see that just opening the file. Okay.
So it freezes the process or the Docker container?
It actually freezes the process. If you have threads, I honestly don't know if it freezes only the thread during the write or the whole process. I assume it's just freezing the write system call, but I didn't really try that. But yeah, it really freezes the process, not the container. So if you have multiple processes in the container, the others continue to happily run. So as I said, you have the data, instead of actually seeing the files, just like I did before, like I touch hello and up hello shows up on your window. Now you just have two big blobs like data and metadata. And if you're so inclined, you can kind of dive into data, but it's really bits of data mapped to the container, so you won't really be able to make anything useful out of it. And metadata, it's even worse. If you try to poke inside metadata, if you change something, since this is the kind of master mapping between containers and actual disk space, if you screw this up, you're basically destroying all your containers. So
Good advice.
Yeah, I mean, in some scenarios you can see what's going on. Like the thing I did, like look, I'm going to touch a file on the left, it shows up on the right. Do this with device mapper, and touch the file on the left, and there's nothing on the right. Everything is done. Okay. So performance. There are two important things here. The first one is that AUFS was smart. Like if you have 100 containers using the same image, AUFS would load a given file only once in memory, and then all the containers will use that file. Great. With device mapper, not so much. Even if you have multiple containers using the same data, because of some low-level details in how the page cache is implemented in Linux, it will still load this multiple times from disk, and it will still use more memory. It's not the end of the world, but it means that if you want to go high density, so high density starting somewhere between 10 and 100 containers, then you should really look at AUFS or overlayfs that have the same characteristics. Another issue with device mapper is that by default, those two files that contain everything, data and metadata, they will be on sparse files. Sparse files, that's again the analogy with the street and the house. A sparse file on Unix system is like when you say to your system, I want a file that is 50 terabytes, but you only have 250 gigs of disk space. Give me 50 terabytes. Fine, this is a 50 terabyte file. We can actually do this now. You can do truncate -- size. So I say I want like 50 terabyte, and that's file of D5. Find too large. Okay, then maybe 5. Right, I can do 5. Obviously, this is a reasonable machine on that file system, and we have 10 gigs. So what happens here? That's really a 5 terabyte file. If we count the number of digits and everything, it will be 5 terabytes. Well, I just asked the system file of 5 terabytes, but I didn't say anything about what I wanted in that file, so it's assumed to be full of zeros. So if I do like less on it, yeah, this is actually zeros, and I can scroll for a very long time, and it's only zeros.
What happens if you try to tail the last and then?
So if I try tail, so I will do something slightly with PV. Yeah, I have PV. I won't try tail because tail will look for line breaks, and there's no line break in it. So I think it will try to show one line of 5,000 of billions of characters. But I can use PV. So PV is it's just like a DD or cat, but it tells the speed. And so here it's reading at like 3 gigabytes per second, which is pretty fast, but we could probably go faster. Obviously my SSD is not going at that speed. It's a KiCast SSD, but not that speed. So when I'm doing that, it's really like the speed at which my machine is able to make up zeros out of thin air. Yeah, I was expecting more, to be honest. But okay, so back on track, I have sparse files just like that. So obviously here, that's a 5 terabytes file, and if I want, I can be fancy, I can open it, and I can see all the way to 4 terabytes and just write hello. I won't do that in the demo because this is already taking forever. I could do that, and when I do that, the system will be okay. I will just take a note that at that specific location, instead of having zeros, I have actual data, and so I will wire this block to actual disk space. Exactly the same thing as device mapper is doing on those virtual devices. This means that when you have device mapper and when your data pool of 3 blocks is on a sparse file, and now I'm in a container and I'm writing somewhere on the disk of that container for the first time. What happens is that, okay, I'm trying to write, oh, but wait, there is nothing here, so device mapper, stop, I have to get some free space somewhere. So device mapper goes to the free pool and say, okay, you need some block, okay, let's wire that block here. So it does some extra writes to keep track of that. And then I have a free block in my data pool. Now the write can goes to the lower layer and goes to the data file. But the data file is a sparse file. So here, it's the file system layer that says stop. This is actually not a real block. I have to allocate a real block, so it will be doing a few reads and writes to find a real block and wire it to that location, and then the write can go through. It means that if you compare a normal machine with a normal disk, and you do a write, and you just do a write, and that's the end of it, in that scenario, in that other scenario, you made maybe 10, 15, 20 disk access just to write one block. So obviously the performance is gonna suck really, really bad. And what makes it even worse is that that's the default setup on most Docker machines. So why? Why even do that? Why the default setup is the worst one from a performance point of view? That's because that's the only one that is guaranteed to work everywhere. Because AUFS, if you're on Red Hat, no AUFS. Here we're using sparse files. It's better to put those things directly on actual partitions and disks, but if you're just installing Docker like that, we won't say, oh, it looks like a good partition here, so I'm going to use it for my space and everywhere we'll see it. So we use those files because it's a pretty safe default. We're not going to erase accidentally data when doing that. It will just be slow and people will have to tune it a little bit. And so the tuning, so the key word here is to remember storage opt. Storage opt is the option that you give to Docker so that you can tell it use that partition or that device to store the containers. Okay. You can even be fancier, and since in that case each container actually has a virtual disk, you can change the size of that disk, you can change the type of file system, and there is some extra fancy options called discard. That's the case. Okay, and some extra links for people who want to have more about device management. I will post the link to those slides on the meetup after. Now let's move to the next one. I'm trying to not waste too much time because people are going to fall asleep otherwise. BTRFS. So BTRFS, so the kind of underlying story was that I think it was Alex Larson, so one of the Red Hat engineers who made device mapper, and very quickly he was like, okay, I know that there's some aspects of this are going to suck, and so let's look already like for the next move, and the next move is going to be BTRFS, because BTRFS is a file system that has this snapshot concept in the core of the file system. It's not like AUFS that sits on top of the normal file system. It's not device mapper that is under the block level. It's directly BTRFS that knows about those snapshots. With BTRFS, you can create a subvolume. So how do we create a subvolume? There is a little tool, BTRFS, and you do something like BTRFS subvol create foo, and now it looks like you've done mkdir foo. You've created directory foo, except foo is a subvolume, and BTRFS will be able to make a snapshot out of it. And when you do a snapshot of a subvolume, you say, okay, I have foo, make a snapshot like a foo snap, and it looks as if you had done cp-a or -r foo snap. So it looks as if you've done a full copy of it, but it's still using a snapshot. So instead of taking 1 hour because you asked it to copy 1 terabyte of data, it's instant, and you can write one copy without changing the other, because then copy and write will happen. So BTRFS is supposed to be the best of both worlds. It's supposed to be the future of files of advanced storage on Linux. The problem is that it's been like 10 years that it was supposed to be the future. So, but no, seriously, there is a lot of work here. That's some really complicated advanced stuff. File systems are hard because when you screw up, you just lose data. So nobody wants that. And BTRFS gets better and better, but it just takes much longer than that. So in practice, if you want to use BTRFS on Docker, then valid Docker has to be on a BTRFS file system. So either your whole machine is full BTRFS and you're good, or if you have some extra partition or LVM running or whatever, you can format it on BTRFS and mount it on top of valid Docker. That's the only scenario where the container images will be visible even when the container is not running, because the snapshots will be there regardless of whether the container is running or not. Okay, BTRFS has some interesting performance characteristics. It's a journal file system. To keep it short, it means that every single data that you write to BTRFS, instead of being written directly, first is written to a journal and then it gets written to the right place. And that means that everything has to be written twice, which means that if you're trying to sustain a high volume of writes, the performance will be twice as bad than with a normal non-journal file system. Oh, there is another thing to know about BTRFS, and that's part of the kind of annoying things with BTRFS. BTRFS works with two types of chunks, data chunks and metadata chunks, and you can think of them as blue chunks and red chunks. And so you have a bunch of free chunks that are like not colored at all, they are like gray chunks, and whenever BTRFS needs to put data somewhere, it has to be either in a blue one or in a red one. And so if at some point it needs to put something in the blue chunk and all the blue chunks are full, then it takes a gray chunk, it paints it blue and it puts the data in it and it continues. The problem is that it doesn't automatically reclaim those chunks. So imagine at some point you've put a lot of things in blue chunks and then you remove those things. So now you have a lot of blue chunks, but they are empty. There is almost no data in that. And you're out of gray chunks and you need to put something in a red chunk, but you don't have any red chunk available and you don't have any gray chunk available. If you were a reasonable person, you could just take like a bunch of blue chunks and put them together and reclaim a few chunks and everything will be good. BTRFS doesn't do that automatically. So you can end in a very annoying situation where you're trying to create a file and it tells you no space left on device, and when you look at it, you're like, what is going on? I have like actual scenario, I have 87 gigs on my file system, but I only have 2.5 in use, and yet it's telling me no space left on device. That's because all my chunks are badly located. Here, that's a less dramatic scenario. I have a 15 gigs file system. I have 4.2 gigs of like actual data in it, but the usage is 6 gigs because I have 1.8 gigs lost in kind of fraction of chunks. So there is this magical command here that basically tells to BTRFS, take all the chunks that have 1% or less of data in them, that's the one here, that's 1%, and put them together basically. If you put 0, it means take all the empty chunks and put them back in the pool of gray chunks. If 1%, 1 here means, so take them, those that are 1% or less of data, put them together, and when a chunk is empty, put it back in the gray chunk.
That sounds like defrag.
It sounds a lot like defrag, right? Which is slightly worrisome, something supposed to be the future of file systems. To be honest, I don't know why is that. I understand the idea of those different chunks because it kind of simplifies the way they allocate the data and everything. I just don't understand why this can't be done automatically.
Right.
Because yeah, it's and I think that maybe, so pure supposition for me, but it's on a normal use case that doesn't happen. But when you do Docker and more generally containers, you do tons of snapshots all the time, and so you end up using the file system in a way that was intended, it was designed for that, but it was not really tested for that. So the performance is good because people have done a lot of optimization and testing on that. The algorithms are good, but that side effect was not really seen. Okay. Now, overlay. So overlay is, well, this slide is becoming less and less relevant, but overlay used to be called overlayfs, and it was a kind of unofficial, unstable thing. And in kernel 3.18, they say, okay, now it's not experimental anymore, let's say it's stable, and let's rename it to overlay, so that people can know that it's not the same thing. This is just a little bit of extra confusion in the file system world. This is exactly like a UFS, except that you only have two layers. You have like the read-write layer, the read-only layer, and that's it. And if you want to have more layers, the way Docker works, so that's if you want to play with it, it's the link to download Ubuntu creating kernel, so we don't care about that. The way Docker deals with this limitation is that instead of layering like 10 layers read-only and then 11th one being read-write, it takes those 10 read-only layers, and from those layers, using hard links, it builds one single read-only layer so that can be used for your container. So it kind of merges all the read-only layers into one single read-only layer, so that you only have those two layers and overlay can work correctly. So it's one of the fastest, with AUFS, it's one of the fastest drivers. It has the same problem with copy up, because again, when you're opening a file that is on the read-only layer, it has to be copied to the read-write layer. However, it doesn't have the stat problem, because when you try to open a file, you don't have to go through all those layers, you only have two layers. Now, VFS. VFS, that one is a little bit special. It's not copy and write, it's copy on copy. So when you do Docker run Ubuntu, it really makes a full copy of the Ubuntu image. So why is that here? Now, two reasons. One reason is that that's a good candidate for porting Docker to new platforms where you don't have a UFS, you don't have overlay, you don't have BTRFS, you don't have nothing. Then you still have VFS, because VFS is just using plain copy, and so there is nothing special here. And it's also great if you are a pretty old-fashioned person and you have zero trust in all those fancy storage things, and you say, I want something that won't eat all my precious data. Then you can use VFS, because it's only using regular copies. It's just could be slow and not very efficient, but in some scenarios that's completely okay. If you have a machine that just runs like a few production containers, and you're not constantly creating new containers and making snapshots and everything, it's completely okay to not have actual copy and write. Right. And the last one, which was added in 1.7, released last week, is ZFS. So ZFS, actually, I should have did that because now it's here. So ZFS comes from the Solaris world. It's supposed to be like the final world in file systems, and like there's nothing after that. It's the ultimate answer to everything related to storage. Actually, it's not. It's not for a few reasons. So first, there is a kind of weird licensing issue. Even though it's open source, it's a different license as the Linux kernel license, so it can't be directly dropped into the kernel like that. And also, it was initially designed for Solaris, and when you run it on Linux, you use something called the SPL, the Solaris Portability Layer, which is something to run Solaris kernel code in the Linux kernel in a way that the Solaris kernel code believes that it's running on a legit Solaris kernel. So that's not exactly native file system code. It has a lot of special case handling, and it can't really be merged like that. And another reason why it's not super widely deployed is that it's really memory hungry. If you want to get good performance from ZFS, you have to throw gigabytes of memory at it. then it will be really fast. It's like this crazy V16 engine. It's going to be really fast and powerful, but you just have to be sitting on a log if you want it to work. So ZFS is great. Snapshots are super fast. It has better performance than BTRFS generally. It has lots of interesting things you can tune. The write performance can be optimized like crazy because it has like multi-layer caching and whatnot. And now it's available on Docker as well. I will skip like the implementation details, but yeah, it works super well. It's extra reliable, fast, but it's not of memory. I will also skip implementation details. If someone is interested, feel free to ask me after. Now, conclusion, because generally the bottom line is okay. What should be using? We've been rambling on for 1 hour about storage drivers and Copyonwrite, but which is the best one? Like I just woke up and I want to know what I should take on and use my service. So because it's not like standard, like so many that you don't know which one to choose from. So the kind of rule of thumb is if you're running a pass, so if you're like, I need to have hundreds of containers in my machine, like per machine, then you want AUFS or overlayfs. If you're running Ubuntu or Debian, use AUFS because it's here, it's stable, it works, and people have been like hammering on it for 2 and something years with Docker, so it kind of works now. If you don't have Ubuntu or Debian, or if you want to be a little bit forward thinking, use overlay because that's the thing that we want to put the energy on in the future. If you
with overlay, it looks like it was merged to the kernel on 3.18, which is like past RHEL 7.
Right. What if
RHEL 7 is 3.10.
So I believe that they might either backbone or do something. So
Like one of their like
clarification on my end, and actually that kind of sad because I was yesterday at the Red Hat Summit, so I should have taken somebody hostage and asked them what I want to do about this.
Okay.
Because my understanding is that they really want overlay to be the thing because the performance characteristics are so much better.
It might be one of their extra package type of
Right.
things. Yeah.
I wonder if they will either at some point make an upgrade to that kernel or backport overlay because Red Hat is also pushing really hard on overlay. Red Hat was initially pushing super hard on device mapper, and I don't know if it's because of the performance characteristics or because of stability issues or because of the phase of the moon or whatever, but it looks like now they want to push harder on overlay. So, but I don't know what's the story like for Red 7. That being said, if you don't have a high density, and more importantly, if you want to have big files in your images and write to those files, then use one of the other drivers. Otherwise, it will really suck because when you start your container, it will make a full copy of this file and you will lose a lot of the benefits of Copyonwrite. That being said, again, the most important thing is really to pick something that you're confident with. If you have some experience with BTRFS because you've been using BTRFS on servers already and you face some of those issues about like data and metadata chunks, then you're probably better off picking BTRFS because when or if it breaks, at least you will be kind of on your turf. You know that thing works. You've been operating for years, so you will be in a better position if bad things happen. If you've been using LVM extensively, then you might want to look at device mapper because device mapper is using the same low-level mechanism. So there again, if you had to fight with LVM and fix some issues, then device mapper is a pretty good bet. Same thing, and if you have used none of those, AUFS is a slightly safer bet because at least the files are here on your disk. So if things go wrong, you can still drop into those directories and see what's there. Okay, I suggest that maybe we should stop here, but if you have questions, we can also continue after. I just don't want everybody to feel like they have to stay here until everybody is over. So let's leave room for some questions, and yeah, in particular, I've got a question about this or about what was the other thing I skipped, ZFS details. We can take this offline after. Thank you.
So, having to deal with massive amount of storage on a regular basis, I can understand why you want to use device mapper, because if you've got a container, you can guarantee the amount of storage that's given to that container. And if they blow past it, you've screwed yourself.
Absolutely.
You know, have a happy day. But with a lot of these other device drivers, I don't see any management of quotas. So if someone does a copy up on something and they, take a bunch of storage that's going to end up zeroing out the file system and cause a bunch of havoc for a lot of other containers, then everybody's in pain. So is there going to be any kind of mechanism to control that quota?
Right. What about quotas? Because as you pointed out, on device mapper, there is an implicit quota, but on the others, so on AUFS, you pretty much have to work on. So you could like say, okay, I'm going to make sure that each container is using a specific UID, and then I'm going to use like the default user quotas. So basically cooperation between the containers and the host system, not so great. On BTRFS, you can assign quotas to subvolumes, so you could assign quotas to containers. I'm actually pretty surprised that nobody has been patching that yet, because that shouldn't be too hard to do. On overlay, that's a little bit like AUFS, so for now it's like, ZFS has quotas too. I just don't know if there's anything to pass them down to ZFS at this point. But the ZFS thing is really brand new. I mean, it's not quite brand new, it's been there for a while, but it's just been merged. So instead of being used just by a handful of people, now it will be used by a few handfuls of people. And we can hope that some people will add those features. So yeah, if storage management like that is really important, device mapper is the best bet for now.
How are you guys looking at Windows? Are you guys planning Windows support at all?
So how are we looking at Windows? So the Windows story is getting like more and more real every day. It's currently DockerCon right now on the West Coast. I don't know exactly what was demoed with Windows. I know there was some demos, and what I know is that it's the same Docker engine, the same code base. Well, obviously when you compile on Linux, you have all the Cygnus and Memphis stuff, and when you compile on Windows, you have something else. I don't know what that is. But on the storage side, I have no idea, because I haven't been running Windows for like ever. I think there is something called shadow volumes that lets us have Copyonwrite on Windows. Yeah. Did you have like a specific question in mind, or?
I mean, the real question is which device driver, for future use, should we consider? Is there going to be new, different ones coming?
It's going to be new, yeah, because, well, except for VFS, all those things are Linux specific. Well, except ZFS in a way, because it's also available on Solaris and FreeBSD. But basically on Windows, we'll have something else. And I think we should know shortly, because Windowsification intensifies. We have there was a demo last month at Microsoft Build, which was really the kind of Docker run hello world kind of. But now apparently at DockerCon, according to Twitter, there was a more significant demo of Docker on Windows. So we'll know pretty soon.
Do some people have different Docker setups for different profiles?
Absolutely, yeah.
Like my databases I'm going to put over here with device mapper and my web applications over here.
Absolutely. For instance, so the question was, do people sometimes have different drivers for different purposes? And yeah, at Docker right now, if I remember well, for the build farm, we're using BTRFS, but for pretty much everything else, we're using AUFS. And we also have a test farm, so that tests like a big matrix of all possible combinations, and then it uses everything, obviously, because that's the point. But I could totally imagine scenarios where some machines would have device mapper, some machines would have AUFS, for instance. all the questions. Well, thank you.